Hello friends, today I will discuss the numerical problems on mesh analysis with dependent sources. In the previous lecture, I covered super mesh analysis with dependent current source. So there it was the current source which was common to the two loops. So we called that as super mesh analysis. In the present case, we do not have the current source common to the two loops. Here we find a dependent voltage source common to the two loops. So the approach is different from that of the previous one. So let us follow the few steps first, and then we apply those steps to solve this problem. And the problem given is like this. So find the current flowing in 1 ohm resistor, that is I by using mesh analysis with the dependent sources in the following circuit. So if you look at this diagram, so this is the 5 volt supply connected in series with 1 ohm resistor. Here there is 1 ohm resistor diagonally connected from here to here, and it is carrying a current called I, small I. Here there is a 1 ohm resistor, and the voltage across that is designated as Vx, and its polarity is also fixed, minus here plus here. And here is a dependent voltage source whose value is 2 into I, is in series with a resistor 1 ohm, and here there is a 1 ohm resistor in parallel with this branch 2I and 1 ohm, and we want what is the current flowing I in this branch. First let me consider the steps to be followed, and then we apply those steps systematically to this circuit. Step 1 is identify the number of loops. If you observe here, this is one loop, this is another loop, this is another loop. Totally there are 3 loops. So we write 3 loops here. Next, second step is assign the loop currents. For this, assign the loop current, similarly for this, for this. Then assign the voltage polarity across each element in the circuit. Then write the equation for small I in terms of the loop currents I1 and I2. The fourth step is write the loop equations and solve for the current I. So these are the 4 steps which are to be followed to solve this problem. So let me draw the given diagram as it is like this. Then so we apply these steps one after the other. First step is identify the number of loops. The number of loops we identify here are 3 loops. This is first loop, second loop, and this is third loop. And next step is assign the loop currents. So if you look at this, this is the loop 1, and its loop 1 current is assumed as I1, and its direction is a clockwise direction. And this is the loop 2, and its current is I2, and its direction is flowing in the clockwise direction. Coming to the third loop, here the loop current is I3, and the current that is flowing in this loop is in the clockwise direction. And after this, we have to give the polarity to voltage across each element. However, if the polarities are already fixed by the problem itself, in the problem itself, here we start writing the or giving the polarity to the voltage across each element as per the current directions. So let me take first loop. This is the first loop. The current is flowing is I1, and this I1 first enters, let us say start here, enters here at the voltage source, then leaves here, but the voltage polarity of the voltage source do not change, so the polarity remains as it is. But whereas this I1 is entering the 1 ohm resistor here, and 1 ohm is a passive element, so the current entering the passive element we treat that as positive terminal, and leaving the passive element we treat that as negative. And this is a voltage polarity for 1 ohm resistor, and it will become voltage drop. Similarly, when it comes here, current enters 1 ohm resistor, so we put positive here, and here we put negative. So we have covered in the first loop 3 elements, this and this and this. So 3 elements are covered. Next, coming to the second loop, we have to give the polarity to the voltage across each element. Here also I2 is flowing in the clockwise direction. And here also we have to keep in mind the voltage source's polarity remains the same irrespective of the current flowing in the element. So let us say the current is first entering the 1 ohm here. And 1 ohm means it is a resistor and it is a passive element. Current entering the passive element will be treated as plus sign, and the other terminal will become negative. Similarly, this I2 enters this 1 ohm resistor here, so we put plus and here we put negative. And whereas the polarity of the dependent voltage source remains same, this is plus, this is minus, it will not change. Same I2 also flows through this 1 ohm resistor. I2 entering the 1 ohm resistor will be treated as plus and leaving the 1 ohm resistor as minus, like this. So 2 loops, voltages, polarities across each element is over. Next, coming to the third loop, so here I3 is flowing in the clockwise direction. Let us decide the voltage polarity across the elements. Let us say I3 is entering this 1 ohm resistor. So this is a passive element. So current entering the passive element, we say this is plus, and leaving the passive element as negative, like this. Then the same current enters here and leaves here. And because it is a dependent voltage source and polarity is already mentioned, so we cannot put a new polarity for this. We have to follow the available polarity for this dependent voltage source. And same current I3 enters this 1 ohm resistor here and leaves here. So current entering the passive element will be treated as positive polarity and leaving the passive element as negative polarity. So in the third loop there are 3 elements, and these 3 elements are given polarity, voltage polarity, and once this is over, then we can write a equation for this current I. This I branch consists of loop 1 and loop 2, and this I direction and I1 direction are one and the same, whereas I2 is flowing in the opposite direction. So the difference of I1 and I2 is nothing but small I. So small I is equal to I1 minus I2. We say this is equation 1. Next step is writing the loop equations or mesh equations. Mesh 1 equation. This is mesh 1. And for this we have to write the KVL equation, that is loop equation. So we start at some point. Let us say start here. In the assumed current direction I1, first we are getting negative polarity, next positive. So it is called the voltage rise. And voltage rise will get the positive sign. So we write plus 5. Next we are getting positive sign here, next negative for the 1 ohm resistor. So getting plus first, next negative means it will be treated as voltage drop in this resistor, so it will get the minus sign, minus 1 into I1. So next, there is one more resistance here, that is 1 ohm, and there is a polarity here, plus minus. In the assumed current direction I1, first getting plus, next negative, means so it will be treated as voltage drop, and voltage drop will get the negative sign. So minus 1 into I1, because I1 equation we are writing, the loop 1 equation, but there is another current flowing called I2, but it is flowing in the opposite direction. So we put I1 minus I2 is the current flowing in this 1 ohm resistor into 1 will give us voltage across this is equal to 0. We have covered three elements, this. So we have three terms here and we equate them to 0. So that is algebraic sum of the voltages around a loop is equal to 0. That is what we have written here. So once we simplify this, we get 2I1 minus I2 is equal to 5, and we say this is equation 2. Next, coming to the mesh 2 equation, this is the mesh 2. So here we start at one point. So polarity is already decided. So in the assumed current direction I2, first we are getting plus, next negative. So we say this is voltage drop. Voltage drop will get the negative sign. So we write minus 1 into I2. Next, again here we have the plus here, minus here. So going from positive to negative, we call that as voltage drop. Voltage drop will get the negative sign. So minus 1 into I2, there is another current called I3 flowing. So I2 minus I3 into 1. So that is the second element. Next, there is another voltage source here. So in the assumed current direction I3 or I2, so first we are getting positive terminal here, next negative. So going from positive to negative, we call that as voltage drop. So we write minus 2I. Next, when it comes to this 1 ohm resistor, first we are getting plus sign, next negative. So we treat this as voltage drop, but there is another current flowing called I1. So we say I2 minus I1 into 1 with minus sign is equal to 0. Means algebraic sum of the voltages around a loop is equal to 0. So we have written 4 terms and equated that to 0. That we can see here. Minus I2 minus I3 minus 2I minus I2 minus I1 is equal to 0. So once we simplify this, we get I1 minus 3I2 plus I3 minus 2I is equal to 0, and we say this is equation 3. And let us go to the loop 3 or mesh 3. This is the mesh 3 again. So we have to write the KVL equation for this. It starts at some point. So let us say we start here. So the polarity that we are getting first is plus, next negative. So the voltage across this will be treated as voltage drop. So it will get minus sign, minus into 1 into I3 is the voltage drop across this 1 ohm resistor. Next we are getting in the assumed current direction I3 here, first minus, next positive. So going from negative to positive, we call that as voltage rise, and voltage rise will get the plus sign. So that is minus 1 I3 plus 2I. Next we have a current I3 entering here, so leaving plus first, next negative. So it will be treated as voltage drop. So it will get the minus sign, minus 1 into I3. There is another current flowing called I2 flowing. So I3 minus I2. So minus 1 into I3 minus I2. That is the loop 3 equation. So once we have this, we can simplify further. So that is I2 minus 2I3 plus 2i is equal to 0, and we say this is equation 4. Now put the equation 1 in equation 3. What is that equation 1? It is nothing but equation small I is equal to I1 minus I2. That is what we are going to put in these equations. So in the third equation means here we put 2 into I1 minus I2. So that is what we have written here, I1 minus 3I2 plus I3 minus 2 into, so that equation 1 is nothing but I1 minus I2. So that is why we have written here 2 into I1 minus I2 is equal to 0. And once we simplify this, we get minus I2 minus 3I1 plus I3 is equal to 0, and we say this is equation 5. Similarly, put I is equal to I1 minus I2 in equation 4. That is, put equation 1 in equation 4. So we write equation up to here as it is, and here we replace this I with I1 minus I2. So we write like this, I2 minus 2I3 plus 2 into I1 minus I2 is equal to 0. Then once we simplify this, we get I2 minus 2I3 plus 2I1 minus 2I2 is equal to 0. So once we simplify this, we get minus I2 here plus 2I1 minus 2I3 is equal to 0, and we say this is equation 6. So equation 2 minus equation 6. Equation 2 minus equation 6 results in like this. 2I1 minus I2 means that 2I3 going to get cancelled. So then we get 2I1 minus I2 is equal to 5. So this is equation 2, and equation 6 is minus I2 plus 2I1 minus 2I3. So we have put equation 2 first, next equation 6, and then we subtract this equation from this. Once we subtract this, we get 2I1 minus 2I1, so going to get cancelled. So minus of minus 2 means plus I2. Here minus I2 is there. So plus I2 minus I2 going to get cancelled. So here minus of minus 2I3 means it will become 2I3. And once we 5 minus 0 means 5 we get. So from this we can get what is I3. So I3 is nothing but 5 by 2, that is 2.5 amperes. So what is this 2.5 amperes? So that is the current flowing in 1 ohm resistor, and this is the question asked in the problem. So we say I is equal to I3 is equal to 2.5 amperes.